Okay, well, it is 6 o'clock. So I'm going to honor everyone's time tonight and get started. So good evening, everyone, and thank you so much for joining tonight. Welcome to EBMUD's monthly webinar series, Water Wednesday. Water Wednesday webinars are an opportunity for EBMUD to deep dive into some of the most asked and hottest topics in water and wastewater. So tonight we're going to be discussing the topic of interest for many EBMUD customers. We're going to be discussing desalination, which is the process of using technology to remove salt from seawater, thereby making it converting it to drinking water. My name is Catherine Horn, and I'm a community affairs representative for EBMUD. I'm going to be facilitating tonight's event, and I have with me my colleague, Joe Volker from Community Affairs, who's going to be monitoring the Q&A function. So just a couple of quick notes. We are going to be recording this event. So by participating tonight, you're agreeing to be recorded. A recording of tonight's webinar will be posted to ebmud.com/waterwednesday within 1 week of tonight's program. Also, we're going to be answering questions after our program, so feel free to submit your questions as we go. Joe is going to be trying to answer some of them real time and then also pulling some of the popular questions for our panelists. If you do have a question for a specific panelist, please indicate that in your question so we know who to direct it to. So with that, I'm going to share tonight's presentation. Okay, Joe, are we good on, or is this showing correctly?
Yes, it looks
great. Great. Okay, thanks for clarifying. Okay, so just a quick review of tonight's agenda. So as we face ongoing droughts in the state of California and here in the East Bay, we get asked a lot, when will EBMUD start doing desal? And it seems like the obvious solution, right? We're surrounded by water on most sides. So first on tonight's agenda, we're going to be addressing that question with a presentation by EBMUD Senior Civil Engineer Hassan Abdullah, who will be discussing where desalination fits into EBMUD's overall long-term water supply planning. After that, we're going to be learning about some of the current challenges and opportunities within desal technology from some of our leading experts. Professor Megan Mauder will be presenting desalination technologies for tapping innovative water sources in an age of limited water supply. And then our evening will be topped off by a presentation by Dr. Jennifer Stokes-Strout from Lawrence Berkeley National Lab, who will be trying to answer the question, desalination and climate change, friends or enemies? So with that, I'm going to introduce Hassan. So Hassan has 25 years of experience in project management and engineering. He has led several water supply treatment and water transfer projects for EBMUD, including the Bay Area Regional Desalination Project. He has a bachelor's degree in chemical engineering and a master's degree in environmental engineering. And he has California professional engineering licenses in chemical and civil engineering. So Hassan, I'm going to hand it over to you.
Great. Thank you, Catherine. Today, I'm going to talk about desalination and how it fits into EBMUD's water supply portfolio. I'm going to give you an overview of EBMUD's water supply and dig deeper into our water supply portfolio. Next slide, please. This is what EBMUD's water supply looks like. We get most of our water from the McKelvey watershed. We have a reservoir called Pardee that collects the water, and then it connects the Pardee reservoir to our East Bay service area through 85 miles of aqueducts. The water is conveyed from Pardee to our EBMUD service area under gravity most of the time. It's very high quality water, requiring only filtration as treatment. We serve about 1.4 million customers. It's 332 square mile service area. Most of our water comes from McKelvey watershed, but during droughts, we operate our Freeport Regional Water Facility, which is an intake on the Sacramento River. It brings Sac River water into our aqueducts and into our service area. Next slide. This is, as I was saying, 90% of our water comes from McKelvey River. 10% East Bay watershed, that we have several reservoirs within our service area. But during droughts, these two supplies cannot support our demand. So we have to get water from a second source or a second intake, which is the Freeport. We get Central Valley project water, that's a federal government contract water, or water transfers that we have to purchase from local sellers, other agencies in the SAC region. Next slide, please. Before we go, our general demand, depending on the year type or season, varies between 120 million gallons a day to 220 million gallons a day. Just to give you an idea, a person generally use about 100 gallons a day. That's both indoors and outdoor, roughly 50%. So 1 million gallons serves about 10,000 customers per day. Next slide. This is what our party intake looks like on a normal and good year. There's plenty of water, very high quality. That intake connects it to our aqueduct, which brings the water to our service area. However, during droughts, it does not look as pretty. Next slide. This is how it looked like during one of the worst droughts we had, 1977. All our work is focused on avoiding a situation like this. Our group division works on water supply, supplemental water supply, and we never ever want to be in this kind of a situation. So we've developed a water supply portfolio that'll guard against this situation. Next slide. This is our current water supply portfolio. The dashed line marks the projects that are already in place. Above that are projects that we've got in place or working on currently. And the line and the projects that are below that dash line are future projects that we are currently working on and may be brought online as it becomes completed. Our first line of defense against drought is water conservation. Our customers have been great this year. As you know, we are in a drought. They've been saving almost 15% of their demand. Our goal is to achieve 70 million gallons a day by 2050. Next project is recycled water. We currently have about 9 MGD supply from recycled water. We are planning to increase that to 20 MGD by 2040. And the third one is water transfers. Currently, we are buying water from Placer County Water Agency, using the Freeport intake to bring it into our service area. We also are working on groundwater, desalination, regional partnerships, and increasing Los Vaqueros project. Next slide. Okay, now we dig deeper into desalination technology. This is kind of an overview of desalination. There are two types of desalination treatment: thermal distillation and membrane treatment. Thermal distillation takes a lot of energy. Only oil-producing countries in the Middle East or surrounding area can afford to do thermal distillation. All the desalination plants within the US use membrane technology. It uses the reverse osmosis process, which is basically a very high quality or high efficient filtration process. The way it works is the reverse osmosis has a screen with very, very fine holes in it. You add the seawater on one side and add pressure on the seawater to push just pure water across the screen to the other side. And these holes, the screens are so fine that it only allows water molecules to go through. It keeps all the salt on one side and produces pure water on the other side. Because it's so fine, and it takes a lot of energy to push that water through the screens and produce clean water. That is one of the issues we have with desal, is that it takes energy. The higher the salt content of the source water, which is highest is about seawater, the higher the energy need for that process is. So that's one point. The other thing is the way it works is, say, if you take 1 gallon of seawater, put it through reverse osmosis, you keep all the impurities and salt on one side, and you produce about half a gallon, 50% recovery of pure water on the other side. So all the impurities and salts stay on that half a gallon, and that becomes concentrated. So if you started with, say, 35,000 milligrams per liter of salt, your 1 gallon becomes half a gallon, your concentration goes up to 70,000 milligrams per liter, double. How do you discharge of that brine solution? That's the reject water. That is another issue we have with Desal. On the pros side for Desal, it's a drought-proof supply as long as it's located on this, uses seawater as the source water. It's unlimited source, Pacific Ocean, generally for us. So it works very well during droughts. It's a proven technology. It has been used all over the world for many decades. So there's been constant improvement on the technology, on the efficiency, and also the energy use. Plus, generally, because it takes seawater as the source of water, it's located on the coastal side. That's where most of the population is. So it's easy to serve the population by the Desal water. The cons are it's energy intensive, takes a lot of energy, and it depends on the concentration of the saline solution that you start out with. Seawater is highest. As you go inland, you may have lower concentration of water or salt in the water, and that's called brackish water. And that can range to half to very high, close to freshwater quality. That's called the brackish water desalination. Brine discharge is the problem. How do you take care of it? Typically, you mix the brine with a local wastewater discharge facility. It has a long permitting process in California. The Carlsbad process, which I'll give you some more details on it, took over 15 years to permit because there are so many issues that need to be taken care of. And the costs, because it's energy intensive, energy inflation is high. It takes a lot of money to produce desal water. Also, if you are producing desal water as a drought supply, you only would use it maybe half the time or even less. That makes it, say, if you use it 50% of the time, other 50% is just sitting there without producing any desal water. So the cost of the water produced during that 50% doubles almost. So cost is a big issue. I just shared a picture of the Alameda County desalination plant. That's what it looks like. Those are all the filters that house the reverse osmosis screens or membranes. Next slide, please. As I mentioned, desalination has been around for a long time. It's been used all over the world. Mostly the largest plants are in areas where it's either dry or has severe droughts, like Australia. In the US, the largest plant is located in Carlsbad. It was commissioned several years ago. It produces 50 million gallons a day. And as it is working very well, producing higher than 50 most of the time right now. The cost for producing desalination water at Carlsbad is around $7,400 to $8,300 per million gallons. Next slide. These are some of the local desalination efforts. Antioch, I'm going to go into that first. It is being done by City of Antioch. They are furthest along. They are in construction right now. They're expecting to finish construction at the end of 2023. They have, because it's located inland within the delta, their source of water is brackish water, which is less saline than seawater, and their production rate is efficient. Is quite efficient. They will be producing 6 MGD out of 8 MGD that they're taking in. So 75% recovery rate. Next is the Bay Area Regional Desalination Project. I'll share a lot more information on it in the next few slides. It's a joint project between 5 Bay Area agencies. EBMUD was the lead agency, and I was the project manager for that project. We looked at a 20 MGD capacity desal plant in Pittsburgh area, East Contra Costa. As I mentioned, I'll share more information on that project. And the third one I wanted to mention was the Marin County pilot study. The study found out that desal is viable in the Bay Area, next to the Golden Gate Bridge. They completed the pilot study, showed that it was technically feasible, but did not proceed with the rest of the project. Next slide. So this is more information on the Bay Area Regional Desalination Project. It's a joint project between 5 Bay Area agencies. We started working on it in 2003, 2004. We did a quick pre-feasibility study to see whether it makes sense or not. It did. We moved into a feasibility study, which was half funded by the state and half by the 5 agencies. So the formula worked really well. That's found that it is feasible. We moved on to a pilot study at the East Contra Costa location. That pilot study completed in 2011. Technically, it is viable, practical, plus we got some design information how to build a desal plant at that location. We moved into, but that pilot study showed that there were certain issues that we needed to tackle, including greenhouse gas, fisheries impacts, and the brine discharge impacts, and so on and so forth. So we did some of the analysis. We completed that analysis in 2013. Then the decision point came in 2013 whether to start this project or not, or initiate CEQA. 2013 was drought, and we had certain other considerations, so we decided not to initiate CEQA. Next slide. Background information, we looked at 13 sites, filtered it down to 3 possible sites, East Contra Costa, Oakland Bay Bridge, Oceanside. And they're all near wastewater treatment plant, so we can commingle the brine discharge. That was the point. And then we chose the East Contra Costa site for further study or pilot testing. Next slide. And the reason we chose the East Contra Costa site was that it had brackish water, so it uses less energy. And there was already an intake that is owned and operated by our partner, Contra Costa Water District. It included state-of-the-art fish screens, so it's all permitted. We could just put our desal facility, pilot desal facility, next to the intake and do the test. Next slide. What did we find from the pilot test? Technically feasible, very high recovery rate, 80+%. Typically, seawater desalination recovery rates are around 50%. During some times of the year, periods of the year, there may be some sensitive species present in that area, so they may be impacted if we pull in water during those times. Brine toxicity, we did lots of tests, including exposing local species to like pure brine without any blending, and there were no effects. Costs were anywhere between $4,300 to $5,500 per million gallons. That's how much it would take to produce the water. EBMUD would get direct delivery, so will Contra Costa. So that's the cost to us. And that includes securing energy through renewable energy. That cost is embedded in the treatment production cost. However, some of our partners are further away, like Zone 7 or San Francisco POC. It would take another $1,300 to $1,500 per million gallons to deliver the water to them. Biggest problem we have, was that because it's inland and within the delta, we needed to use water rights, and Contra Costa has that water rights. However, during droughts, that water right could be curtailed, meaning cut by the state. They may not allow Contra Costa to use that water right to pull water for the desal plant. So our next step would be to find out how we can install or construct a desal plant that is drought proof and can be operated during all times of drought. As you know, 2013, 2014 and 15 were severe droughts. We kind of moved on to taking care of the drought situation that faced us during that time. So we haven't quite answered that question yet. Next slide, please. So we are continuing to work on all of the strategy projects that are available to us. We're leaving no stone unturned. We want to build a resilient and sustainable water supply for the future through diversification. And that includes desalination at that East Contra Costa site or some other location. Well, thank you all. That was the end of my presentation.
Fantastic. Thank you so much, Hassan. So now I'm gonna have the pleasure of introducing our next speaker. So Professor Megan Motter is an associate professor of civil and environmental engineering and senior fellow in Precourt Energy Institute and the Woods Institute for the Environment at Stanford University. She directs the Water and Energy Efficiency for Environment Lab with the mission of providing sustainable water supply in a carbon-constrained world. Ongoing research efforts include developing desalination technologies to support a circular water economy, coordinating operation of decarbonized water and energy systems, and supporting the design and enforcement of water energy policies. Professor Motter also serves as the research director for the National Alliance for Water Innovation, a $110 million Department of Energy hub addressing U.S. water security issues. The hub targets early-stage research and development of energy-efficient and cost-competitive technologies for distributed desalination of non-traditional source waters. Professor Motter holds bachelor's degrees in civil and environmental engineering and history from Rice University and a PhD in chemical and environmental engineering from Yale University. Before joining the faculty at Stanford, she served as an Energy Technology Innovation Policy Fellow at the Belfer Center for Science and International Affairs, visiting scholar at the Mozaffar Rahmani Center for Business and Government at the Harvard Kennedy School of Government, and associate professor at Carnegie Mellon University. So thank you so much, Dr. Motter, for being here. And now I'm going to turn it over to you.
Great. Well, thank you so much for having me. It's really a pleasure to be able to talk to a broad audience of people who obviously care very deeply about resiliency of their water supplies. And I'm actually here on behalf of this National Alliance for Water Innovation, which is based right in your backyard. Its home is at Lawrence Berkeley National Lab, and it represents a consortium of institutions that span a whole host of different Department of Energy national laboratories around the country, as well as hundreds of different kind of academic institutions and innovative companies that are all working together on this grand challenge of how do we secure water supply in kind of a changing climate where drought is likely to become more frequent, where we're seeing increased demand for traditional water supplies, and also where water quality is becoming an important issue in more and more places. So what I want to do today is talk to you about how desalination technologies can help us tap a whole host of non-traditional water sources. Hassan mentioned in particular a number of surface brackish water sources as well as seawater sources. And I want to kind of couch this as a talk that encourages you to think about sources beyond what we would think of as traditional seawater sources. Okay, next slide, Catherine. So there is, as Hassan mentioned, a really long-standing tradition of using water desalination around the world. You may not realize it, but 2/3 of Israel's drinking water originates as seawater. That will soon be 90% once a final plant comes online. And they have a tremendously resilient water supply because of that association and dependence on the sea. We also have desalination here in the US and here in California, especially. So there's a Carlsbad desalination plant in Carlsbad, California, that provides San Diego with 8% of its water supply. Unlike the Israeli case, where the vast majority of water is provided through desalinating seawater, in the case of San Diego, it's a much smaller fraction, but the advantage is that it's drought-proof. The second advantage is that it really caps the costs of water on the open market. And so there's financial reasons and there's climate resiliency reasons to pursue desalination as part of a broad water supply portfolio. But I think that both of these examples have opened the question about whether desalination is relevant beyond these wealthy coastal communities, and really how a whole swath of the US might tap desalination technologies to secure their water supplies. The argument I want to make today, briefly, is that, one more, Catherine, if you don't mind, is that desalination is not just a technology for tapping seawater. It's really a technology for tapping a whole host of different non-traditional waters. And in particular, that it allows us to tap wastewaters and other water sources that we've typically discarded to enable a circular water economy that is low cost and also delivers low carbon water supplies. I'm very fortunate that I don't have to give this talk in its entirety. The third speaker is Jennifer Stokes-Strout, who is also a member of the National Alliance for Water Innovation and a key lead in assessing the decarbonization implications of seawater desalination. And so I'm going to let her talk a little bit more about that low carbon element. Next slide, please. So I'm certainly not unique in thinking that it's important to apply desalination technologies to a broader set of non-traditional water sources than just seawater. I think the environmental engineering community and water treatment community widely recognizes that securing water supplies across the US is actually going to require us to tap municipal wastewater, agricultural wastewater, industrial wastewater, and even really quite impaired waters, things like oil and gas produced water and stormwater. So the EPA has a water reuse action plan that came out last year and has done a lot of work in trying to quantify what is the magnitude of these non-traditional source waters and where might we use that treated water beneficially. That doesn't necessarily mean we're going to use this water for drinking water supply, but it might offset water demand for cooling, for instance, or we might see on-site reuse of industrial water instead of taking water in manufacturing processes, using it and then discharging it either to the environment or to a municipal wastewater treatment facility. Okay, so I will say, though, that while we have some great technology, things like reverse osmosis, which were highlighted in Hassan's presentation, but also are very core to the technology deployed in Israel and here in Carlsbad, there's still need for lots of technology innovation to make this vision of a circular water economy possible. And in particular, I think we're going to need innovation that is very specifically focused on the source waters that we are trying to treat. Next slide, Catherine. Right. So NAUI is really set up as a sort of early stage technology development organization that is trying to focus on reducing the cost and energy intensity of non-traditional source water treatment and desalination. And so we needed to prioritize where we would invest our research dollars. And we did an early survey of the energy intensity of a whole host of different non-traditional water sources and really learned two things. The first is that the energy intensity of treating these non-traditional waters is often 3 orders of magnitude higher than it is to treat a traditional freshwater source. So there is going to be significant increases in the cost and energy intensity of treatment itself. There's also a lot of variation among the different non-traditional source waters that we might tap. So you'll notice here that I haven't actually plotted the absolute energy intensity, but what I've done is I've plotted the relative energy intensity, so the energy intensity normalized to the thermodynamic minimum. The thing you need to know, and I think Hassan explained very nicely, is that the absolute energy intensity is going to increase as the salinity of the feed water increases. But when we're hunting for technology opportunities, one of the things we quickly noted is that seawater desalination via reverse osmosis processes is one of the most thermodynamically efficient separation processes that exist today. And so there was actually a lot more opportunity for impactful innovation in treating, in sort of figuring out how to treat some of these other non-traditional source waters. Next slide, please, Catherine. The second realization that we had as a team was that energy intensity of water is a very strong function of conveyance of that water. So we think about water as sort of being supplied in 3 different steps. The first is transmission of that water, so taking it from the source to the treatment facility. The second is the energy embodied in treatment. And the third is the energy embodied in distributing that from the treatment plant to individual water users. And what we realized very early on is that in a typical water system, such as the one pictured here, it's not uncommon for transmission and distribution to account for 80% or more of the total energy intensity of water supply. And you'll see here with the line on the furthest left of this plot, for a typical surface water fed system, your treatment energy intensity is very low, but your transmission and distribution energy intensity can be somewhere around 0.5 kWh per cubic meter. It's actually very high in places that are hilly. So when we think about Northern California and coastal California especially, what we find is that we're often spending as much energy to sort of treat, or sorry, as much energy to distribute water to high elevation sort of areas, service areas, as we would to desalinate that water. And if Catherine clicks a couple more kind of clicks forward, this line actually demarcates a place where the total energy intensity would be the same order of magnitude. The total energy intensity of treating that water on site and reusing it would be the same order of magnitude as kind of trying to pump it all the way up to a provider or a water user. So across the municipality, there are actually many places where on-site water reuse could be much less energy intensive, even if the treatment step of that reuse is more energy intensive. So this all, the set of revelations that it made sense to focus on non-traditional source waters other than seawater, and that this kind of element of sort of distributed desalination was going to be important because of the energy embodied in transmission and distribution, led us to sort of a hypothesis as a research organization. And that was that, we see these declining treatment costs as you increase the operational scale of a facility. You get economies of scale in treating water. Next, Catherine. But we have diseconomies of scale when we're transporting water. As I just showed you, there's the further you're going to transport water, the higher you're going to pump that water, the higher the transport cost is going to be. And so what we see, next, Kevin, is that today's plant sizes tend to be built in this kind of like 50 MGD size or so, and that that is cost optimal for current plant designs. But our hypothesis is that well, we are never going to be able to change the amount of energy it takes to overcome gravity. Water is heavy and gravity isn't going anywhere. What we could do is dramatically lower the cost of water treatment. Catherine, if you could click forward a couple more slides. And in doing so, in dropping that cost of treating at the small operational scales, that the whole kind of optimal size of that plant starts to come down, and the costs are going to start to come down as well. So we believe that we can effectively reduce the cost and energy intensity of non-traditional water reuse through small scale and distributed desalination. Just in summary, our hub has a couple of sort of key mission areas. At a very broad level, we are aiming to secure water supply through energy efficient and cost-effective water desalination. We believe that desalination is a critical unit process for water reuse. We also believe that there's a diverse set of non-traditional water sources, both natural water sources and wastewater sources that can be desalinated and reused. And this includes seawater and brackish water that Hassan mentioned earlier, and then municipal, agricultural, industrial power, mining, and oil and gas sources as well. The key, though, is that the technology innovation to get us there, the technology isn't fully there for small scale systems, and those cost reductions are going to happen through innovation in 6 key areas: autonomous, precise, resilient, intensified, modular, and electrified desalination systems that are small scale and readily deployable. We believe that if we can achieve an A-prime system, we'll see significant reductions in the energy and cost of water transport, that will allow us to achieve cost reductions through modular and manufactured systems, and that will also achieve cost reductions because of reduced time to deployment and increased supply resiliency. Catherine, you can keep going forward a couple more. I want to end simply by saying that we've also done a lot of work in assessing what the actual costs of these small scale systems are. And what you'll notice is that there's a wide variety or wide distribution of costs today. These are today's costs. But we are really aiming to develop a set of technologies that would bring these costs down quite significantly. And I'll turn that over to Jen then in the next presentation. I'll just go through these a little bit more quickly and say that Jen has been really instrumental in helping us to publish these baseline studies for those costs and some technology roadmaps for how to get us there at a sector level. So with that, I'll just conclude and pass it over to Jen, who I think is going to chat a bit about the carbon implications of desalination.
Okay, thank you so much, Dr. Motter. That was super informative. We really appreciate that. So let me just introduce our final speaker today. So you queued her up quite nicely, but I'm going to introduce Dr. Jennifer Stokes-Drought, who so appropriately named, right? Dr. Stokes-Drought studies the economic, energy, and environmental implications of infrastructure systems at Lawrence Berkeley National Lab and UC Berkeley. She focuses primarily on innovative water systems, specifically evaluating trade-offs and synergies between conveyance, treatment, distribution, and management of potable water, recycled water, wastewater, and stormwater. She is also interested in understanding the interdependencies between water, energy, and agriculture and how they will be affected by our changing climate. She is currently serving as the deputy lead for the National Alliance for Water Innovation's Data Modeling and Analysis Research. Jen has a bachelor's in science from the Georgia Institute of Technology and a master's in science and PhD degrees from UC Berkeley in civil and environmental engineering. So with that, Jen, I'm going to turn it over to you.
Thanks, Catherine. Megan already queued me up pretty well to let you know that I am going to be talking about the relationship between desalination and climate change. And really a little tongue-in-cheek title, which is, are they friends or are they enemies? Hassan already kind of started us off telling us that the energy intensity required for desalination is one of the potential cons associated with this technology. And Megan updated that to say, it depends on the water. It depends on, there are some things it depends on. And we're going to talk a little more about that. But all of that energy has implications for climate change. And so here we are looking, experiencing drought every few years, looking for new sources of water, looking out, most of us are within a close driving distance to a saltwater source and thinking, what are we going to do for our future water supply? It's kind of an obvious answer to think we might desalinate. But if we're choosing something that then releases a lot of extra carbon in the atmosphere, driving more climate change like that, that could be potentially problematic. So I want to talk today about how that relationship is evolving, in part due to some of the innovations that Megan has talked about in her talk, as well as some others. So, Hassan already told you that energy use is one of the critiques of desalination. So just to give a couple of examples, back in our last drought in 2015, there were, pushes for more desalination in the state. And even at that time, there's a quote, environmentalists are skeptical of desalination because they're expensive and they use a lot of energy, and also some environmental impacts on marine life. And even more recently, when we were thinking about a big desalination plant in Huntington Beach, which ultimately was not given a permit to construct, people were saying energy is a key factor in deciding whether this should be built. The energy needed to run that desalination plant was roughly the same as what it would take to run 3,000 households for a year. So that's not nothing. Next slide. And these are real concerns. Desalination does use a lot of energy. Megan already told you a little bit, like it just takes more energy to get salt out. This graph came from a report written by the Pacific Institute based in Oakland. And they published it in 2013, comparing the electricity intensity for many of the water supplies that are used throughout California. And the three starred sources on this graph all involve a desalination step. The top one is seawater, ocean water. In the middle, you see both membrane treated recycled water. A lot of that is for potable reuse. That was the term Megan used. And then the one below it is this brackish water desalination, which both Hassan and Megan have alluded to already. Next slide. For reference, EBMUD's water supply, on average, some research out of UC Davis determined that on average it takes about 1,200 kilowatt hours per million gallon. But depending on where you live, at the bottom of the hills or the top, it can really be, for a particular customer, it can be anywhere from 400 to 5,000. So more than an order of magnitude difference, depending on where you are. And also, as Megan alluded to, that top end is in the range of where you see desalination processes, the energy intensity for desalination processes. It's a similar amount. Next slide. Not all desalination is equally energy intensive. So this graph may look familiar because it pulls from the same set of case studies that Megan showed you in terms of the cost. She showed you the cost for these case studies. I'm now showing you their relative energy consumption, and those are often related, but there are other costs to be considered besides energy, obviously. And there's a huge variability, and it depends on the source of the water, how salty it is, what other things are present in the water, how large or small the treatment system is. So does it benefit from economies of scale? The biggest ones that stick out on this graph are Gila River Power Station, which has to get rid of all of the water. They are not allowed to discharge any water, so they have to kind of boil it all off. It takes a lot of energy. And the other one is a semiconductor manufacturer who needs really high purity water. So they use a lot of energy to achieve that. Next slide. The three of these that are relevant for urban areas like EBMUD are, on the left circle, brackish water, which varies largely based on quality and how you dispose of the water in the end. The middle one is municipal reuse, so reusing wastewater. These vary depending on how the water is used by customers, and then some of the treatment processes can impact how much energy is used for those. And then that last set is the seawater desalination. Those tend to be closer together and more similar in the ways they use energy, and that's largely because we've just spent a lot of time optimizing those systems. Next slide. But even for seawater desalination, the energy consumption is changing over time. We are improving our ability to make it more efficient, to recover energy from the process. So this graph shows the trend in energy consumption between 1980 and 2020, and it has a downward trend. So we've improved a lot. So next slide. If you take the portion of this graph between 2013 and 2020, roughly now, and you translate that onto the graph I showed you earlier, you would see that that seawater desalination electricity intensity has, even in that 7-year period, probably shifted to the left, as is shown in that lighter blue box. So we're improving the technology. We do expect for seawater desalination or reverse osmosis that that's probably going to flatten out. There's not that much additional potential to make that more efficient, but we have a lot of potential for these other water sources, as Megan said. Next slide. At the same time, our greenhouse gas emissions associated with this treatment are going down. They're changing with time. So this first blue bar that you're seeing from 2013 is also a number that I pulled from that Pacific Institute report that I showed you for the electricity consumption. Next slide. Or no, yeah. This next blue bar is my estimate of what that same number would be using 2020 data. So instead of using the energy assumptions that they used in 2013, I used the number for Huntington Beach, which was lower. But on top of that, I used PG&E's grid as it was in place in 2020, which is has a lot more renewable energy on it than it did in 2013. And so that change in the electricity grid provides a significant reduction in the greenhouse gas emissions associated with that desal-related electricity use. Next slide. We can project that further out using data from the National Renewable Energy Lab. They really think about how the grid is going to change in the future. And I'm showing you 3 different cases here. The blue bar is their mid case, what they expect is most likely to happen. But the dark blue diamond and the grayish diamond are really showing you 2 other scenarios that are on the high emission range of their projections and the low emission range of their projections. So regardless of where we are in that boundary, you can see that compared to 2013, when a lot of this critique of desalination was really being popularized or discussed, you know, we're going to see something like a 25 to 30%. That the greenhouse gas emissions by 2050 will be 25 to 30% of what they were in 2013. And that's without any changes in the technology. That's just based on changes that are going to happen in the grid. Next slide. We still do need to make improvements to the technology, and Megan has alluded to these. There are certainly opportunities to improve efficiency and energy recovery, especially from water sources that are not seawater desalination. Next slide. We can do more renewable energy than even the grid would allow us. Hassan said that in EBMUD's plan, they were thinking about using purely, like investing in their own renewable energy. That would improve that performance dramatically. Next slide. We also have the ability to use, well, at this point, desalination doesn't do a great job of providing demand response. And demand response is the way that we adjust how we use electricity depending on how much energy is on the grid. And colloquially in the energy world, we call this the duck curve, because we have to ramp down our fossil fuel use when solar and wind increase during the day, and then we have to ramp it back up in the evening when those renewable energies are not available anymore. In the bottom left, you can see this demand curve for September 6th, right after Labor Day this year, when it was super hot and we all got really intense messages on our cell phones telling us to turn off our energy. And so if we had desalination systems that could respond to that alert so that we weren't using that high fossil fuel dependent energy during those periods, we could really reduce the carbon. And right now we can't do that. And next slide. And the last thing is that there are these other innovations that Megan alluded to that NAUI is focused on that could contribute to decarbonization. I'm not going to talk about all of them, but we are looking at ways to make systems more autonomous so that they can respond automatically to things like demand response, to prevent sort of failures in the system, so that we can just operate more efficiently and in a more optimized way. And another thing we could do is produce chemicals on site. We can produce acids and bases on site with electrochemical production. And that would prevent us having to use a lot of trucks to transport chemicals that are produced with fossil fuels from somewhere else, which also could reduce our carbon footprint for our water. Next slide. That is it. My final statement, are desalination climate change friends or are they enemies? I think they're maybe still in the frenemy range at the moment, at least for the conditions that EBMUD is looking at, but I think the future is potentially very bright.
Well, hopefully we can put desalination in the friend zone at some point. So thank you so much, Dr. Stokes-Drought and Megan and Hassan. Thank you guys. So we're going to open it up for questions in just a minute. I just want to give a brief reminder. We are going to try to end right at 7. So we're going to get through as many questions as we can. And I know Joe's been trying to answer some of them real time. He's going to help pull a few of them. I am going to just quickly go through this last couple slides. So if you do have any questions that don't get answered tonight, please feel free to email us at waterwednesday@ebmud.com. Any additional questions or something that might come to you later. Also, please join us for our next Water Wednesday, which will be on November 16th, 2022, another webinar at 6 p.m. And this one is going to be focusing on seeking the source and some fantastic presenters who have been exploring EBMUD's watersheds. So those are going to be really interesting. So with that, I'm going to open it up for questions, and Joe is going to give us our first question. And let me just stop sharing the PowerPoint. Okay.
Yeah, so we did get quite a few questions, tried to answer a lot of them. The first one is for Professor Motter. When looking at smaller facilities, have you factored in the long-term cost to operate and maintain those facilities?
Yes, these represent costs of actual facilities that I showed that are small scale and installed at existing sites. Not all of them were as small a scale as we might hope to achieve going forward, but those are all-encompassing capital operation and maintenance costs for the facilities. I will say I think that there's a lot of opportunity to innovate in the operation and maintenance space, where it's not realistic to have a professional operations staff of the type that you would typically see at a water treatment facility like EBMUD would run. And so we need ways to use lots of the automation capabilities that have been developed in the water space, and really see those deployed for small scale systems to help operators sort of make more intelligent decisions about when an on-site person is necessary and when they're not. And I think that the second thing is that we can't think about just downsizing or downscaling our existing technologies. We need to design technologies that are inherently more robust and resilient to fluctuations in water quality, resilient to outages, et cetera, so that the need for that operator is diminished.
Right. The next question is for Dr. Stokes-Drought. We got quite a few about the electricity costs of this. So as electricity is expensive with regard to CO2 emissions, has a combined nuclear power solution been considered? Waste heat can assist with vacuum boilers, while high pressure osmosis could be used for grid following this, keeping the reactor at 100%.
Yeah, and that is a solution that we see in other parts of the world more. And so there's a lot of research into it. I don't think it's one of the configurations that we're really focused on in NAUI. We've kind of, as a state, we're not really moving toward nuclear energy at the moment, for better or worse. So mostly we hear about desalination coupled more with solar, is just more what we're hearing about. We're also not seeing a lot of these vacuum boilers. That's not really how we're doing desalination right now. So those are certainly like opportunities that exist, but it's not what we're expecting to see here.
Okay. The next question we have, it's open, it wasn't directed at anybody, but it says, besides carbon energy issues, what are the most significant environmental impacts generally associated with desalination projects? Are such impact concerns only relevant to desalination of seawater?
I'll take that. I mean, desalination, the problems with our environmental issues with desalination comes from taking water from the source water through the intake. That has fisheries impact, but that's common with any intake, whether it's desalination on the backside or not. So that's there. Energy intensive carbon, that's one, and the discharge of brine is the third issue. Those are the three issues primary issues with desalination.
And the discharge of brine is an issue pretty much regardless of what water you're desalinating. That one is, the intake from marine life is really only for seawater desalination, or if you have a surface brackish water system. But the brine and to a lesser extent, the energy and carbon are the same for all of them.
I think one thing I'll add is that in a seawater installation, you are pulling in a much higher salinity feed than you would be in a municipal water reuse scenario. And so the quantity of brine that you're going to end up with is like much smaller when most water reuse settings. And Hassan alluded to that a little bit when he was talking about the Antioch system. That is a brackish surface water, and while its salinity fluctuates quite a bit depending on sort of seasonality, et cetera, you're able to recover quite a bit more water and discharge quite a bit less brine. So I think it really depends on what your source water is, and its impact is also going to depend on what the receiving water is, or what the receiving entity is. If you're taking that all the way to a minimal or a zero liquid discharge, you might envision a setting in which actually you have very, very little discharge at all. And that is not a reality for most desalination facilities today. I don't want to pretend that it is. It's certainly a direction that there's opportunity for lots of innovation around. But I think that the primary solution is simply generating less brines by tapping lower salinity sources to begin with.
So I think we're getting close to 7, so this will probably be our last question. While there are several promising modalities, they all seem to relate to long-term solutions. What happens if California experiences 2 to 3 year drought years in succession following what we are currently experiencing?
Well, I'll speak to that and just say, I think one of the things that we've realized as a hub is the value of a diverse water supply portfolio. That diversity helps to build resilience into the system. And part of that diverse supply portfolio is tapping kind of existing traditional freshwater sources, as well as these non-traditional sources. And it's also in having a diversity of treatment technologies to tap those non-traditional sources. So some treatment technologies are simply going to take 10 years to do design studies around and permit and build and get into operation. There are probably a whole suite of other technologies that could be deployed in a 2-year time frame or a 6-month time frame. Package systems like the kind that was installed at Fort Bragg that can come online very quickly and respond to drought in sort of an as-needed basis. The operating costs of those facilities might be higher. They might not be designed to be as efficient as your large seawater desalination facility, but that actually helps to reduce the overall cost of water supply. And I think I saw one question in the feed that was also kind of focused on, what does this mean for water costs writ large? we are not suggesting in most places in the US that seawater desalination wholesale replace our wonderful existing sources, right? So you're talking about marginal additions of water supply. So, you might use desalinated water for 5 to 10% of supply. And yeah, that marginal cost might be higher than your average water bill, but it's not like your whole water bill is going to start to become the cost of that desalinated water.
Okay, fantastic. And thank you so much. So we are right at 7 o'clock. So I want to thank our fantastic speakers tonight for your presentations and answering all of our questions. That was such an informative presentation by all of you. And we really are so grateful that you could be here tonight. I also want to thank our participants tonight. We had almost 200 people participate. So yeah, great turnout. I know a lot of people are very interested in this topic. So if you didn't get your question answered tonight, again, please feel free to email us at waterwednesday@ebmud.com and we'll try to get you an answer. And we hope you join us next month for our next Water Wednesday. So again, thank you all and have a fantastic evening.
Hi, everyone.
Good night.
Thanks, everybody.